Okay, thank you so much for this opportunity to give a presentation at this big stage. Thanks to the QMAT, and particularly thanks for putting this thing in JNU, which is also my alma mater. So it's always nice to be here. So anyway, so the presentation is about, this is the title, Transport Through a Nodal Surface Semi-Metal Superconductor Junction in Absence or Presence of Light Irradiation. And this is just I just flash a picture of my college just to show you, that's it. And the important part is the acknowledgement. This work is done by Bhaskar Pandit. He's my doctoral student, just submitted his thesis, and he's also a faculty in some college. And financially, this is supported by this ANRF grant, this work. So the content of the talk is that I'll first briefly discuss about topological semi-metals like Weyl semi-metal, nodal line semi-metal, or nodal surface semi-metals, and then particularly with more emphasis on nodal surface semi-metals. And then there we'll talk about the light radiation, the flow K approach there. And then we'll go to the quantum transport problem, where we consider a S-N junction, where the N is the basically not the normal metal, but in a nodal surface semi-metal, and then summarize. So typically we know that the topological semi-metal means that the conduction and the valence band, they can meet in discrete points, lines or surfaces in momentum space, and depending on that we can have different kinds of topological semi-metals. Topological because they can have some boundary states, boundary modes, and we can have can calculate some numbers like Chern numbers, Jack phases, etc. in different cases where we can get some non-zero quantized values. The dispersions are generally linear, immediately away from the nodes. That's why we use Dirac physics. This is very basic things. And I have just shown some typical Hamiltonian of these three kinds: Weyl semi-metal, nodal line semi-metals, and nodal surface semi-metals, where this is QZ, and this is Q rho, which is like Qx squared plus Qs squared, square root of that. So if you can just give a plot like that, and this orange one is the dispersion spectra, and this blue one is a constant energy surface. So you can see that for zero energy, you can have both Qz and Q rho to be zero for this case. For this case, for energy to be zero, we have to have a single values of Q rho, but Qz non-zero. And here you can have like all values of Q0 at Qz equals to 0 to get your zero energy. So these are the three different scenarios for these three different kinds of semi-metals. Okay, now when we talk about the topological material, we have to talk about this topological invariant or topological phases. So there can be two different kinds of systems, for gap systems or gapless systems. For gap systems, the things is, I think, comparatively easier, so that we can calculate this Berry connection, where u lambda is the wave function, Hamiltonian wave function, and then we can just get a full integration in the Brillouin zone and get some value of non-zero value for our topological phases, and that can also be converted to this. Let me just go there. It's too far close. And then 2D, you can go to the surface, you can go to this Berry curvature surface integral. These are the standard things where this omega is given in this form. And for 3D, you can have the integration path is arbitrary. So you can generally be taken around high symmetry points. Typically for TRS broken systems, you can have a 3D Chern number, which has three components, and these components can be given as some surface integral of omega, which is the Berry curvature. Now for the gapless systems, because we have just gapless systems like in 3D, we have this topological semi-metals, so what we have to study here. The problem is the node in the Brillouin zone. So basically when we calculate that, we always do the integration around the node. So and that's been done in 2D, like in graphene, this is the direct node. About the direct node, we take the Berry connection and get the integration to get the value of the topological invariant. And in 3D, we have to So depending on the nodes, so the node in 3D, the node can be 0D, 1D, or 2D. So depending on the dimension of the node, we have to decide, we have to find an envelope, enclosing envelope that doesn't touch the node, and then on that envelope we basically define the topological charge or topological invariant. So for a wild semi-metal, because it's a zero-dimensional nodal point, so we can consider, we have to cover that up. So we consider surface. Basically, the enclosing envelope have a dimension DC called its codimensionality. It's given by D minus D node minus 1. D is the dimension. D node is the dimension of the node. So that's it. So from there you can see for wild semi-metal we have a surface here for the enclosing envelope. And there we can do this omega integral, thus Berry curvature integral, to get the topological invariant. For the nodal line semi-metal, it's a 1D node. So we have a 1D envelope which goes like that. It should ring through the nodal line. And then there we just do the Berry connection integration to get the value of the topological invariant. And for nodal surface semi-metal, because the node is 2D, so it basically, this gives us the point. So at the point we have to calculate the topological invariant. So basically what is done with some little abuse of terminologies. Generally 2 points are considered, one inside and one outside, and then the Berry fluxes are calculated in these two surfaces parallel to this actual nodal surface, and the difference of that will give us the topological invariant. Now one thing for the gapless fermions, we have to remember that there is this Ninomiya no-go theorem, which says that the total number of topological charge within the Brillouin zone should be 0. So if we have some nodal surface or these things, we have to make sure we have to have in a number so that overall the charges can add up to 0. So now nodal surface semi-metal, there the conduction and valence band touches in a nodal surface, but that surface not necessarily has to be in a single energy. We can have, for example, this is coming from some Hamiltonian, we'll talk about that later, but this is just a plot for the dispersion at ky equals to 0. There you can see, from there also you can take another cut. You can see that for different, you can have situations where the nodal surface is actually, this one corresponds to the nodal surface. This is for ky equals to 0. For different ky also you can have this kind of conduction band and valence band matching for all the kx values. So the main point is that they can be, they need not have to be at the single energy, they can vary in energy, the nodal surface. Now how we can get these nodal surfaces? They can become because of some particular symmetries. You can have global internal symmetry where some Z or Z2 topological classes possible. You can have a combination of unitary or anti-unitary symmetries like sublattice or PT symmetries, which can have some Z2 topological classes, or you can have some non-symmorphic symmetry. So we'll talk about this last one. So non-symmorphic symmetry means it's a combination of point group symmetry and a half lattice translation. So it can be given in this way. So you just it's like a screw rotation. You rotate as long as you just go advance. It's not like rotation, a product of rotation and translation. It's both of them going together. So a picture is shown here. There. So this is one rotation, and then also translation. Another rotation, also translation. Okay. So from here you can see that. By these two steps, it just comes back to this initial configuration. This is a so it's rotating as well as it's advancing. It's like that. So now, if let's first consider 1D Hamiltonian. So how we can have this non-symmorphic symmetry? The corresponding matrix can be given by this 2x2 matrix. So you can see that G square kz turns out to be e to the minus I kz times sigma naught. So that means it gives, if you just apply the operator 2 times, you just get a translation along z direction by one unit lattice. So this gives me that my G can be of this kind. So now if this G can be a symmetry of the system, we have to have this G inverse equals to H, and that gives me more condition on the Hamiltonian. It says that H cannot have a sigma 3 term. It can be a combination of sigma 1 and sigma 2. So you can write it in this form, and then with this condition, now for this condition to match, we have to have a gapless point or gapless point in the system to satisfy this thing. So this non-symmorphic symmetry says that there can be a gaplessness, there is an essential gaplessness. But then with that additionally, if you just put some inversion symmetry of this kind or this kind, then that basically pin that gapless point at the Brillouin zone center or at the Brillouin zone boundary. So depending on which one you choose, you get this one. So from there you can get a continuum model. You get a simple continuum model of this kind. So where this Q is defined in this form. So about kz equals to pi is the nodal surface. And then from this 1D system, you can go to a 3D system, just like a bunch of this kind of 1D chain that makes a 3D system. So your 3D Hamiltonian can look like this thing. So it's the same as this one, but only the coefficient now has some kx, ky in the argument. So now, but this, whatever I just said, this one, if we just do the construction for the topological charges, just like if you take 2 points, one above and one below the nodal surface, then calculate the Berry fluxes, we see that they are same. So basically, if you take the difference, that's 0. So from that definition, it doesn't have any topological charges. You can have a different kind of topological charges, which these people have studied, where they considered this Hamiltonian, the continuum Hamiltonian. This is basically coming from this tight binding Hamiltonian, where they have studied it in acoustic metamaterials. So there you can see, you can do the similar construction of the Berry fluxes, if they can calculate above and below the surface. The difference is non-zero, so that gives me some non-zero topological invariance or topological phase basically. And because of this theorem, no-go theorem, we here always remember that we have to have some other topological entities to make the overall charges 0. Now because this thing is, because of the non-symmorphic symmetry, the way we are, this is put here, this is staying at the Brillouin zone boundary. So if it is staying at the Brillouin zone boundary, it doesn't have a partner to have an opposite topological charge to make that 0. So in this case, actually what they have two more y points. So like the -2 and +1, so overall topological charge becomes 0, something like that. Now in these systems we can study radiation, but just by some time-dependent electric field or magnetic field. The usual Floquet theory we can use, and so H becomes Ht plus T. So this is the time periodic drive. So for that, we can design a stationary Hamiltonian, just the way this is done, and we can study the stationary Hamiltonian in the high frequency limit. It's like a high frequency expansion. And the two Hamiltonian we just studied. So if we have some linear electric field of linear polarization, that ends up giving us something Hamiltonian like that, which doesn't have any gap at all. So it doesn't have any, like, not nodal surface, not nodal line, or nodal y point. But the other one, the one which are more interested, there if we just put some electric field, both for linear and circular polarization, we can get some nodes there. Apart from whatever we had already, we also can have some, actually this is nodal line, this was my student's poster, so I just forgot to change that. Here we can have one nodal surface as well as one nodal line, and in this case for circular polarization we can have one multi-y point other than the nodal surface. So that's all for the first part. Okay, so I'll not just go for the conclusions, it's the same thing. So with that Hamiltonian, the second Hamiltonian we just talked about, we just studied this quantum transport problem. So it's considered a junction with a nodal surface semimetal with S-wave superconductors. So as we know that generally for a normal metal superconductor junction there is anti-reflection. So if the electron goes from the normal direction and falls on the interface, then one hole reflects back. So that's the anti-reflection. and it can be of two kind. If my Fermi energy is very far from the node, then basically both the holes and electrons stays in the same band, the conduction band, and there you can get this retro and reflection. And on the other hand, if it is very close to zero, then you can have some interband transition also. There you can have some peculiar cases. So these kind of things can happen. So now we will see how what we can find in this particular system when we have a nodal surface semi-metal instead of this normal metal. So with this Hamiltonian, this is my delta function, the superconducting pairing function, and also we have this step potential where the positive x side is the superconductor and the negative x side is the nodal surface semi-metal. So we consider this BDG equation because we are dealing with both electrons and holes, so these are just the equations for two limits where mu is very large and mu is very small. These are the wave functions, these are the dispersions, and this is for the normal side and this is for the superconducting side. And then we just got these things by matching this boundary condition, and then with that we can get these plots. So here this is the angle of incidence. So first of all, here because we are considering this nodal surface semi-metal Hamiltonian, we kept our QZ not 0, because if we put the QZ at 0, we are exactly at the nodal surface and the Hamiltonian just identically becomes 0. So we consider very small values of QZ so that we can get some non-trivial features close to the nodal surfaces. So we kept QZ equals to 0.1. It's not written here generally, and then for that we calculated. So my theta E here, what is the incidence? This is this is on the xy plane, this angle of incidence. So it's going on the x direction. So from there, the angular definition is the deviation is the theta E. So if we with the theta E, you can see how the reflectance is varying. So for the normal incidence, we have this full anti-reflection, and then it goes to it falls gradually like that. If you keep on increasing these values of theta E for the sub-gap cases. If you go to the super gap case, it first of all doesn't start from the 1 value because this is a super gap case. We don't have this full anti-reflection for energy greater than delta. But then when it falls down to 0 as we keep on increasing theta, it shows some non-trivial behavior. So it suddenly shoots up and then stays there for some time and then again comes back to 0. Now this is, we're just trying to find why these things happen. We just looked at the mathematical formula. We saw that in this regime, basically in this superconducting side, these two waves which are given by these ones, these numbers, these px plus and px minuses, they becomes imaginary. So they becomes imaginary means these are also showing some decaying mode. So that is actually increasing the anti-reflection in this part. So that's we understood mathematically what happened. And then here, this is the case for when mu is very small. When mu is very small, very close to 0 energy, we can see some non-trivial behavior because all the other behaviors are kind of standard. We have seen in different cases also. Now this is because for mu very small, here in this case you can see here this eta 1, here this eta 1 can become imaginary. So that that gives some difference in feature, and then we have got these things. And then when E becomes larger, so that it can go over, so it no more becomes imaginary, those eta 1 and eta 2, and then it again comes back to the standard behavior. And then this is showing the tunneling conductance. So here we have varied the values of the state potential strength starting from 0 to some 30 delta value. And we can see for Vs equals to 0, it starts from 2. So Vs equals to 0 means I think there is no normal reflection, only anti-reflection is occurring. So that's why it starts from 0, and then it starts reducing, because effectively with increase of energy, the Cooper pair production reduces, because delta minus E is reducing. And then you have this resistive decay when E is greater than delta. Now, if we keep on increasing this Vs value, then normal reflection starts occurring again. So that reduces the end reflection. That's why this G also reduces. So we can understand these things in this way. Now for this one, as we keep on decreasing the values of mu from 100 delta, you can see this is reducing. This thing is reducing because what was the reason? There's some reason I forgot that. It's written here somewhere. So, but this is the behavior, and you can see it's not. You don't see any plot here for very small values of energy because of that same reason that we saw that for small values of mu, here mu equals to 0 for small values of mu, and for small values of energy, you are getting some non-trivial behavior in the reflection coefficients also. So this is because of that. So then we consider this irradiation on that system. So my Hamiltonian changes. So for the circular polarization, we can have apart from the nodal surface, we can have some multi-while point in the spectrum, and because of this changed with this changed Hamiltonian, we can see these are the reflectance plots for large mu and small mu values. These four are for the large mu values, and these four are for the small mu values. And this is the tunneling conductance, where you can see the Andreev reflection becomes very small in these cases. That's why in the subgap cases, the tunneling conductance becomes almost 0. And then if you keep on increasing the strength Q naught, which is given by this quantity, then you can actually completely perish that subgap conductivity. This is for the circular polarization. And then for the linear polarization, also with this changed expression for the Hamiltonian, we can get a nodal line in addition to the nodal surface what it already had. And then these are the plots for reflectance, where you can see for small values of Qz what we are considering, Qz equals to 0.1. The Andreev reflection for the subgap cases is very small, just like in the previous case for the linear polarization. But then here, if we keep on increasing slightly the values of Qz from 0.1 to 0.2, then this suddenly shoots up here, and then we again starts getting this huge Andreev reflection in these cases. So that is pretty much it. And so the conclusion is basically saying the same thing. And then of course there are some applications if we can realize these nodal surface semimetals and get junctions with that with superconductors, and to get the quantum transport. So that's it. Thank you so much.
Thanks for keeping the time. We actually finished quite early.
Okay.
Time for questions.
You mentioned in the Andreev reflection plots that there is a critical angle. What does that signify?
Oh, critical angle means I maybe didn't plot that. So with the angle of incidence, we have this this angle of Andreev reflection, which is smaller than the angle of incidence. Now, if you keep on increasing the angle of incidence, at one point of time that becomes so both are increasing. So there is a critical values of angular incidence. After that, you will not get the Andreev reflection. So that is the critical.
Any other questions?
Yeah, this is the equation. This is the equation. So in the critical case, this sine theta e becomes 1, and so that the theta sine theta a becomes 1, and the corresponding theta e is the critical angle.
Okay. Delta you have considered. This is the pairing amplitude, right?
Oh.
So is it?
Yes.
It is on-site pairing or something else?
The delta is the superconducting pairing.
He's asking, is it on site or just nearest neighbor? If you put it on a lattice, that's what he's asking. Yeah.
I don't know. Means I don't know.
Any other questions? Okay. If not, let's thank Shantuki again.
Thank you.